Hi everyone, my name is Gabe and I'm delighted to be here to present our paper, Effective Point Size and Opacity Adjustments in Scatterplots, on behalf of myself and my co-authors Andrew Stewart, Paul Warren and Caroline J. So today I'll first briefly run through the research motivation before moving on to some background work, the methodology of the paper, the results and the discussion. Firstly, the motivation of this work, or as I like to call it, Scatterplots are cool. So I applied for my PhD during COVID and I was motivated by the fact that people such as my parents, who were not familiar at all with statistics or data visualizations, saw and were expected to understand visualizations pretty much every day. I knew I wanted to help make visualizations easier to understand for people who don't study or design them, and so I chose to focus on scatterplots. So I chose to focus on this kind of visualization for a number of reasons. Firstly, they are common enough that most people are at least vaguely familiar with them. I didn't want to have to spend too much time explaining esoteric visualizations to lay people. Secondly, there is evidence that people's interpretations of them is rapid, under 500 milliseconds according to some papers. Critically, they are used by non-experts. And finally, there is evidence that people underestimate Pearson's R. So I've included a plot here on the right that illustrates this. If estimation was perfectly accurate, we would see both lines follow the diagonal. Whereas in reality, we see that while people are quite accurate when R is low, and when it is very high, this accuracy falls off around the midpoint, and it does so according to the curve you can see here. So we've previously completed work which shows that we can change visual features, namely the sizes and opacities of points on scatterplots, to change people's estimation of correlation. In 2023, we showed that lowering point opacity can increase levels of underestimation, that lowering opacity as a function of residual distance can decrease levels of underestimation and therefore increase accuracy, and in a separate paper that year that doing the same with point size also increases accuracy, interestingly to a much greater degree. So these findings led us to ask ourselves what would happen when we combine these manipulations. So you can see some plots there. These were the experimental stimuli, however we will get onto this more formally in a few minutes. I'm now going to briefly run you through some background material. So changing the opacities of points on scatterplots is an established technique and has been used extensively to address issues of overplotting. So when we try to plot data sets with very large numbers of points, the overlap between points can make trends difficult to see, and previous work disagrees on the effects of doing this on correlation perception. Changing the sizes of points is often used to describe an additional third variable to the standard 2. These are commonly referred to as bubble charts. Again, there is disagreement in previous work about the effects of this on correlation perception and people's estimates of Pearson's R. So the perception of correlation is thought to be based off the width of the underlying probability distribution, although this is an open question that is difficult to answer given what we know at the moment and the current methodologies that are available to us. There is, however, ample evidence that changing visual features in graphs is able to induce changes in people's perceptions of those visualizations. Additionally, we know that opacity and size changes can bias perceptions of means and can have effects on, among other things, speed perception. So we'll now run through the methods that we used in the current paper. So our methodology was very simple. This was intentional in order to facilitate the rapid collection of large amounts of data with lay participants. So these are groups that have often very varying levels of experience with statistics and graphs. So participants were shown scatterplots of the type you see here and were asked to use a slider to estimate the correlation displayed. And you can see that slider that they were asked to use at the bottom of the slide. All our stimuli were generated using ggplot in R, so the GitHub repository associated with this paper includes R scripts that do this. In order to set the opacity and sizes of the points, we used the following equation. So point size or opacity is equal to 1 minus b, which in this case b had the value of 0.25, to the power of a particular point's residual. We used a 2x2 fully factorial design, and all 150 participants saw 45 of each plot for a total of 180 experimental items. We chose to crowdsource all of our participants. This not only meant that data collection could be completed in a matter of days as opposed to weeks or months, it also meant that we could easily recruit representative samples from the populations that we're interested in. We're interested in lay populations, largely because a lot of work has been done on graph perception and visualization with, for example, graduate students and people who are familiar with statistics, whereas the motivation for this work was thinking about how people who don't have experience in those areas interpret visualizations. We used linear mixed effects models to model the effect of scatterplot design on correlation estimates, and we included a battery of pre-experimental tests. Graph literacy via a simple 5-item self-report measure, dot pitch, which helps us get an idea of the physical sizes of scatterplot points on participants' monitors, and point visibility. So it was key for us that we avoided removing data, as this would be, for one, a very obvious way of biasing perceptions of correlation up. Not that that's a problem, but it is dishonest. It changes the story that is told by the visualization, and therefore we wanted to avoid doing that. And this meant obviously making sure that people could see all of the points, as we are playing with small sizes and low opacity points. So I'll now briefly talk you through the results. So as you can see from this plot, all but one of our conditions still resulted in the underestimation that we would normally expect with conventional scatterplots. Typical orientation here refers to when the numerical value of the feature in question, so the value used to set its opacity or its size, is decreased as a point moves away from the regression line. Inverted orientation simply refers to the opposite. So when we have a combination of manipulations that is typical or inverted, these are referred to as congruent pairs. When it's typical inverted or inverted typical, these are referred to as incongruent. When we combine typical orientation plots, participants overestimate the correlation quite dramatically. Note that these are estimation means over the range of R values used, so we'll look more closely at estimation across R values in the next few slides. When we combine inverted orientation manipulations for both factors, as we would expect, we saw large degrees of underestimation. We're going to examine these two conditions more closely in the next slide, but we won't talk in detail about the incongruent conditions. Firstly, the congruent inverted orientation plots, which had the form that we see here on the left. On the right, we plot the R value along the x-axis from 0.2 to 0.1. This is the objective R value that we set. On the y-axis, we plot the level of estimation error. Here, overestimation occurs above the horizontal dashed line, while underestimation occurs below. We can see that the shape of this curve is similar to that of the standard estimation curve. Now we take a look at the congruent typical orientation plots, which take the form that you see here on the left. Here we can see that we have overestimation for the overwhelming majority of R values, which suggests, given the previous results, that there really is little limit to how much we can bias estimates one way or another using simple visual features and encodings. So we saw no significant differences between our other two incongruent factors, no effects of graph literacy, point visibility, or dot pitch on correlation estimation performance. In our modelling, we did find a significant interaction term, which suggests that, contrary to what we expected, the combination of size and opacity decay functions in scatterplots is not additive. So through this work, we provide evidence that using both size and opacity manipulations together produces dramatic effects. These effects are stronger than we predicted, and through comparison with our previous work, in which we used opacity and size manipulations alone, are stronger than either manipulation used in isolation. Our correction, however, is still not perfect, but testing these manipulations together, as we have done here, allows us to compare them with the manipulations in isolation. So the plot here displays what we refer to as power, which I will walk you through now. As you can see, we have the objective R value again along the x-axis. Power on the y-axis refers to the correction that would be needed at each R value to produce a perfectly accurate estimation curve. The dashed line you can see here represents this power value, which we've calculated using previous experiments that used conventional scatterplots without manipulations. Starting in the middle, we can see that when we only use an opacity manipulation, we get some correction. On the right, using only a size manipulation, we get quite close to correcting for the underestimation effect. Again, this is not perfect, but it is better. And on the left, finally, the results from the current paper, we can see that when we use size and opacity manipulations together, we've really overshot and have caused overestimation for most values of R. So we've included the integral of each power curve over R at the bottom of each plot, along with the difference between that integral and the integral of the required power curve to numerically demonstrate how close or not we're getting. So regarding future work, there are a number of avenues that we can take this. We could examine the effects of manipulations using only particular R values, which might allow us to build a bigger picture of the contributions that size and opacity decay functions have. There exists also an opposing overestimation effect in negatively correlated scatterplots, and this suggests that we might be able to use our techniques that we've established to address this. And the equation that we talked about earlier that we used could also change. There are a variety of parameters that could be different, the value of B. There are different ways to get this effect, whereby things reduce as they move away from the regression line. So it may be the one that we chose was not ideal and something else would work better. And finally, we could also use different encoding channels, such as point orientation. Finally, I'd just like to point out that this research was carried out in an open and reproducible manner. This QR code here takes you to a GitHub repository that includes a fully executable paper built using Quarto. We use Docker to recreate the computational environment and allow you to recreate our analyses and our modeling. Thank you for listening to this presentation.